Right, everyone, good morning. So today we're going to jump into the 2023 MSD 780 exam. We're going to focus specifically on questions 1 and 2, so that deals with the initial dynamic analysis. Once we've done that, in the next section, we're going to look at question 3, which is then going to focus on the optimization of the mechanism that we've covered in questions 1 and 2. So just to give you a breakdown, last year's exam total marks was 100. This year will probably be the same. It consisted of 3 questions. Question 3 had some short questions. Now, last year what we did is we actually performed the exam using the AMS system. So students had to submit on the AMS portal, on the AMS UP portal. This year we're going to probably do it a bit different. So I was thinking of rather just using answer books and then using the script, collecting that afterwards. But overall, the general premise of the test should remain the same. There will be a section which focuses primarily on dynamic analysis, and then the following section will be optimization. Okay, so the mechanism that the students had to use last year was this Gough-Stewart machining platform. And I call it a machining platform because in a CNC environment, you would place some sort of an end effector or a cutting tool on this platform over here. So this platform AB that you have. And a Gough-Stewart platform, if we're going to look at the 6 degree of freedom version in a moment, this is just the planar version. Essentially what it has is 3 actuators over here, and this is now the planar version. Each actuator allows the load that is placed on the platform to be distributed along each actuator. So you get better load distribution and accuracy capabilities than when you compare it to something like a serial manipulator. Now, to just give you an idea of how the 6 degree of freedom goes. So this is actually a real model, and what you'll notice is that the motion of the system is pretty accurate. It can control all 6 degrees of freedom of motion. So you have translation in the X, Y, and Z directions, and then you also have rotation about each of those axes. And in this case, we now have 6 actuators. We also configure them in this case in 3 combinations. So on this base platform that you have over here, you have them grouped together. Just go back a bit. So they are grouped together in pairs of 2 on the base platform, and then also over here on the moving platform. On the moving platform, we also have the spherical joints, and then over here on the base platform, we have universal joints, and these joints then allow for that 6 degree of freedom motion. Now, once we move over to a planar degree or a 3 degree of freedom Gough-Stewart platform, then any of those spherical and universal joints simply become revolute joints. So in this case, we have revolute joints at points A and B, and then also over here on the base, which we are only going to denote as ground at C, D, and E. Okay, so figure 1 shows a schematic representation of a Gough-Stewart platform that will be considered in this exam. In our case, we're then also going to focus on the trajectory of this plate over here, this moving platform that we have. So figure 2 shows a prescribed straight line path as it gets executed by the GSP. The dashed lines show the configuration of the GSP at the start point of the prescribed path, and the solid lines show the endpoint configuration of the GSP. So we are essentially having it move along this straight line, and they also give us some additional information at a speed of 0.01 meters per second or 10 millimeters per second. Then we are also provided with 3 driver constraint functions, and they are defined to control the 3 respective actuator lengths. So we have actuator length AC, which is a linear driver function with respect to time, and then we also have actuator lengths AD and BE, which are then quadratic functions with respect to time. And we're going to look at how we can utilize these functions using the different function types within DAP-BC as well. Then they also say that an incomplete DAP-BC model of the GSP can be found, and this is then made part of this DAP-BC dynamic Q hybrid workbench. GSP_B is the model that we're going to focus on. So in our case, The model is named GSPB, and it contains the following input files which are already populated. So in animate, in bodies, and in points. Then question 1 was edit the following DAP-BC input files and simulate the mechanism for 40 seconds with a reporting time step of 0.4 seconds. Now we're going to use this to obtain the results, but before we do that, if we just want to run a quick animation and see what happens to the system, we can probably use a bit more coarse reporting time step over here. Okay, so that is ideally what you want to do. First, set up your system, check from a static perspective, does the system's configuration look correct? Once that is done, you can run an animation on a bit of a more coarse reporting time step, check if you get the correct trajectory planning, and once that is done, then you can go into the results. Okay, so in our case, the input files that we need to change is in_forces.m, and they say that we need to take into account the weights of the bodies. There's also then a constant friction force acting on the center of gravity of body 1. Okay, so this is then given over here, F friction. So this would probably coincide with a case where you have some sort of an end effector that you place at the center of mass over here. So you have some sort of a resistive force when it's cutting through the material, or when it has some friction due to stabilizers placed at this point. Okay, once we've edited the in_forces.m file, then we're going over to the in_functs, in_joints, and in_uvectors input files that we also have to change. And we'll also notice that these three input files are essentially connected to one another. So whatever we define under in_uvectors, we're probably going to use that under in_joints to specify our kinematic joints over there. Okay, so without further delay, let's then jump into our input files. So I first just want to have a look at the files that were given to us. So the in_animate, I think the other one was in_points, and then in_bodies as well. So if we start off with in_animate, you'll notice that you have these GC0, 1, 2, 3, up to 10. So these are all of the animation points that we consider. And if you have a look at the values over here, it's -0.1, -0.08, all the way up to 0.1 again. So these are essentially the points that are going to that are given just to check the actual motion of the system. So we'll have a bunch of dashed or dotted points that the platform should follow when it executes its trajectory. Then for the bodies, we have some lines and rectangles as well. So these are just to denote the actuators that we have. I think for body 1 as well. Okay, so body 1 is not defined. So it's in any case just going to construct a line between the center of gravity and then the points A and B. Okay, and then X min and X max, Y min and Y max are given as per usual, just to define the animation plane as well. So we can assume this is also fine. Then in bodies, we can also see that these are simply constant values that are given as input. So for bodies 1 through to 7, each of their masses, moments of inertia, and then their coordinates and starting angles are also given. Okay, so we can assume that this is also correct. Just to perhaps illustrate with the actuators what we do. So you'll see we have the platform body, which is body 1, and then each actuator is broken up into two bodies. So the top body ensures that there's a revolute joint between the platform body and then the actuator, while the bottom over here, the below body, ensures that there's a connection between the actuator and the grounded revolute joint. So we have in total 7 bodies, so 2 bodies per actuator, 3 actuators, and then this moving platform body 1 as well. Now, since we break each actuator up into 2 bodies, we also need to note that there has to be a connection between these 2 bodies. And if we perhaps have a quick look at linear actuators, so if I jump in over here and just say linear actuator, and we can perhaps have a look at something like this. So this is just a hydraulic actuator that we have. In this case, as the fluid flows into this pocket that we have over here, the actuator itself is going to move out. If we reduce the amount of fluid in here, this linear actuator is then going to go back inside. So essentially what we can assume is that this acts as a sort of a sliding joint. And in the case of DAP-BC, we simply model this as a revolute joint, or sorry, a translational joint. So we just need to note that connection between the two bodies of each actuator as well. We're going to define that under the injoints.m input file as well. Okay, and then lastly, we also have endpoints. So in this case, you'll see that it's named CP0. So C just denotes the actual point that we're working with. In this case, it's point C. P just indicates that it's a point, and 0 indicates the body that we are considering. So on a revolute joint, we know that it's a connection between two bodies. In the case of point C, we know that it's between body 0 or ground and then body 5 as well. So we expect to have a CP0 and then a CP5 as well. And we can see there's a CP0. If I scroll down a bit, there's a CP5 as well. In the case of point A, we're going to have point A on body 1, A on body 2, and then A on body 3 as well. D will once again be between point 6 and point 0, E between point 0 or body 0 and body 7. Point B will simply be between body, point B will be between body 1 and body 4 as well. Okay, so all of these have then also been defined within the endpoints file that we have over here. All of them are grouped together in this points list that we have at the end. So this then brings us to the first file that we want to go and change. So you'll see enforces.m has been given as an open function. There's nothing provided inside, but we do have the information given over here. So they say for the enforces.m file, we need to note that the weights of the bodies are taken into consideration, and then we also have a constant friction force acting on the center of gravity of body 1. So first thing that I can go and define over here is then weight. So I'm just going to say S1 is then equal to the force structure. Then S1.type is equal to weight. And if I don't specify any other parameters for this type of force, then it's going to take the gravity as 9.81 meters per second squared, and the direction will be in the negative y direction. So that is fine. We don't have to worry about changing any of those parameters. Okay, once this is done, then it says there's also a constant friction force acting at the center of gravity of body 1. So if I perhaps forgot how to define this, I can always go to the user manual that I'll also have available. So I think this would be DAP-BC user manual. If I open this one up, the one that we are interested in is enforces. So I'm just going to scroll up. Right, so over here in this table, they give us the different types of forces that we can specify, the input requirements, and then also just a breakdown of what it entails. So in my case, I probably want to use this F over here. So I have to give it a body index and then the actual force as input as well. So this is a constant force defined in the XY frame. And we can see from the question as well, it's defined in the XY frame, F friction X1, F friction Y1. That will be applied continuously on the body. So in our case, we are working with a constant friction force, so that's fine. So we can use this type F force. Now, just to understand how we give the F as an input, you'll see if you could just go up to the previous page in table B4, it says when you specify F, you have to give it as an X and a Y coordinate over here, separated by a semicolon. So that is essentially what we're going to do for this F friction that we're going to specify. So I'm just going back over here and now I'm going to define S2. So S2 is then also a force structure. S2.type will then be type F for a constant force, and then I just need to give it S2.IB index. So they said it's applied on body 1, so I'm just going to type in 1 over here, and then S2.F is equal to, and now I just have to go and check what the values are. So the first one is minus 50.0 and then minus 86.603. Separated by a semicolon, so minus 86.603. Okay, so now I've defined both the forces. Now I just have to go and group them together over here in this forces that I have over here. Okay, so then in forces is done. Then the next one that I have to go and change is in functs, in joints, in U vectors. So I'm going to start off with in joints because we want to define the functions. So the functions that are given over here, it's ideal to rather define these things at the end. So I'm first going to focus on the simple joints that I can go and specify. So in this case, I'm going to start off with the revolute joint. So I have revolute joints at points C, D, and E, and then also at points A and B. Okay, so in total, I have 1, 2, 3. At point A, it's going to be 2 revolute joints. So one between body 1 and 2, one between body 1 and 3. So there is 1, 2, 3, 4, 5, 6 that I have to go and specify. Okay, so if I jump into in joints over here, I'm just going to start off by creating perhaps just a section over here which is called revolute joints. If I do this, I can just say revolute joints. Okay, so this should help me to just keep track of which joints I specify. So I'm going to start off with revolute joint, let's make it C. So the first thing that I want to say is J1 is a joint structure. J1.type will then be a revolute joint. And then I just have to give as input, if I go back to my user manual over here, I scroll down to the in joints. Then you'll see in this case, I have for a revolute joint, I need to specify the IP index and the JP index. Okay, so to do that, I'm first going to say J1.IP index, so point index I. And I now know that the revolute joint acts between bodies 0 and 5. So I'm perhaps going to use CP5 as point index I. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So index 9 that I want to use over there. And then I also have index 1. Okay, so I'm just going to say IP index is 9. And then J1.JP index is equal to 1. Then I just have to go and do the same for revolute joint D. So I'm just going to type in J2 is equal to joint structure. J2.type is once again a revolute joint. J2.IP index will then be point D on body 6 and then point D on body 0 as well. So DP6 and DP0. So that would be, if I look over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 2. I'm just going to say 10, and then J2.JP index is 2. Right, so then just the same for all of the other revolute joints as well. So revolute joint E, J3 is a joint structure, J3.type is a revolute joint, then its IP index is going to be, if I go back, so that's the last one, so that would be 11, and then 3 as well. Then I just have to go and do it for the motion platform as well. So at points A and B, so revolute joint A, and I think this will be 1 with 2. So J4, and I just go and check its IP index again. Okay, so in this case, I'm working with bodies 1 and 2. So if I go back to in point, this would be over here, so point index 4 and then 6 as well. So I'm just going to say 4, J4, that JP index is 6. Okay, so if I'm fairly confident in the way that I specify the previous, I'm just going to copy some of these over, and then I just have to remember to update the naming. So A1, A3, and then this one we can make B1, I think this would be B4. And I just have to go and update the indices of these joints as well. Okay, so for A1, A3, I'm still going to work with point 4, but then for JP index, I have to go and change this. So this would be the next point over here. So AP3 is then 0.7. And then for B1, B4, I'm just going to change this to J6. Okay, that looks good. So if I then say the IP and JP indices, so that would then be 5 and 6, 7, 8. Yeah, so 5 and 8 that I'm working with over there. Right, so now I've defined all 6 joints. I can note as well that I defined up to J6, so this is fine. Now next up, I just want to go and define the connection between the 2 actuator bodies for each actuator. So in that case, it's the sliding joints that I'm going to specify. So I'm just going to create a new heading over here, call that translational joints. Okay, so in this case, there's going to be 3 of them. One that exists between bodies 2 and 5, another between 3 and 6, and the last one between 4 and 7. So before I go and define this, I just have to understand what I need when I specify a translational joint. So I need an IP index, a JP index, so 2 point indices on the different bodies. And then I also need an IU index and a JU index. So these 2 pertain to the in U vectors files that I need to go and manipulate or modify. Now, if I quickly check at what the definition is in figure B6, if I have point 0 as my first point index, then I also need U0, which is defined on the same body. In this case, we can call it body 0. Then I also have B1, so that's the second point, and U1, both of them then defined on body 1. Okay, so in my case, I am then going to need 1 unit vector on each of the actuator bodies for each actuator. So if I look at this one, I'm going to need U5, U2, U3, U6, U7, and U4 as well. Okay, so I'm going to start off actually going over to the in U vectors file then. And I'm just going to specify them in this file, the unit vectors. Now if I just check, in U vectors should be, I think before this. Right, so for the in U vectors file, when I specify a unit vector, I need to specify the body index on which I'm specifying that unit vector, and then also its local axis. So or a local unit vector on the system in accordance with its local coordinate axis. So in my case, it would probably be the easiest and the best, since I have the translational joint acting along this line, to also specify my unit vectors in line over here. So U5, I'd like to align with this Xi5 direction, and then U2, I want to align with the Xi2 direction. And then I can do the same with 3, 6, 4, and 7. Okay, so I'm going to start off by first defining on body 2. So if I say U2, I'm going to make it a unit structure. U2.body index, and this will then be on body 2. And to align it with the Xi direction, I'm just going to say U2.u local is then equal to 1.0 and 0. Just want to check that I still use a semicolon. Yeah. Okay, so then that is fine. Then I can go and do the same with U5. So I'm just going to copy this over, just change the name over here to U5. And this is now on body 5. Then I do exactly the same for bodies 3, 6, 4, and 7. So I'm just going to maybe make a few copies of this, 3, 6, and 4, and 7. Okay, so I also defined it in such a way that U2 and U5 are called after one another, so subsequently. In this case, when I then call the unit vectors, it just makes it a bit easier to go through the list 1, 2, then 3, 4, then 5, 6. So once I've done this, I just have to group them in that order as well in this U vectors list. So I'm just going to make this U2, U5, U3, U6, U4, U7. Okay, so now I have all of the unit vectors that I need to specify those translational joints. So now I can jump in, and I'm going to define J7 as the first one, as the first translational joint between bodies 2 and 5. So this will just be a joint structure. J7.type will then be equal to TRAN, which is just a shorthand for translational. Okay, so then I give J7.IP index, and if I perhaps work with, let's maybe start with body 2. So in that case, I want to use a point that is on body 2. In this case, I can see that A2 will probably be the best. So I have A2 and C5 that I can utilize together with the unit vectors. So in this case, I'm just going to start by saying AP2 is the IP index. So if I head to in points over here, so that would be index 1, 2, 3, 4, 5, 6. So then I define over here 6. And then I just have to give the correct IU index as well. So this is then the one on body 2. If I go back, that is the first element that I have over there. So I'm just going to say 1. Then I specify J7.jp index, and that will then be C5. So if I head to in points, C5 will be, so this is 6, 7, 8, 9. Okay, so 0.9 that I use over here. And then J7.ju index is then going to be the unit vector on body 5, so that is the second element that I have. Okay, so now I'm just going to do the same for the other 2 translational joints. Just going to create copies of these, and then I just update this to J8. and then I just go and check the IP, JP indices, and then also the IU and JU indices. So if I look at this one, we used AP2, so now I want to use AP3, so that would be 7, 1, 2, 3, 4, 5, 6, 7, and then I think the other one is D, so that would be 8, 9, 10 that we want to use. So 7 and 10, I'm just going to say over here 7, JP index is 10. Since point 7 then lies on body 3, I'm going to use U3 and U6, so that's points 3 and 4, or rather indices 3 and 4 over here. Okay, and then lastly, joint 9 is just going to be J9 everywhere. And then we can also go and check its point indices, so this will be between point B on body 4 and point E on body 7. So BP4 and EP7 that I'm looking for. So in this case, it would be 1, 2, 3, 4, 5, 6, 7, 8. And then the second one is 9, 10, 11. So 8 and 11. So two indices that I use over there. Right, and then if I check, this is just the last two indices, so that's 1, 2, 3, 4, 5, 6. I'm just going to say 5 over here and 6 over here. So I place 5 under IU index since it corresponds to the point on body 4, and then JU index, which is on body 7, corresponds to the point on body 7. So both of them are indicated with the J over here. Right, so now I've defined all of the kinematic or the reaction joints. So if I quickly go back to the paper, then you'll remember that we also had this specification with regards to the actuators. So actuator length AC, AD, and BE, each of them have a driver constraint function that is given. So these driver constraints I want to specify after I've specified all of my reaction constraints or reaction joints. Okay, so in this case, just to understand which type of joint I need to use, I can go back down to the in joints part. Okay, so you'll notice over here we have the last two entries is then the driver motors that we can use. We either have this relative rotation driver, in this case it's a rotational motor or actuator that requires an analytical function, or we have the relative translation driver, and this is a translational motor or actuator that requires an analytical function as well. In the case of the relative translation driver, I also need to give the point indices on the different bodies as well as the function that I'm going to utilize. Now, in my case, I do want to use the relative translation driver since I'm working with a translational actuator or a linear actuator. So in this case, if we go back, we can clearly see that in this schematic, these actuators have to basically translate along these axes over here. So that is why I then use the relative translation driver, and it coincides with the definition of the actuators as well. Okay, so to define them, I'm first going over to the infuncts file. I first have to actually go and set up the different functions that I'm using. And to do this, I can head down to the infuncts part that I have over here. All right, now to define the type of function that I'm using, I just need to consider the actual form of these analytical functions. So we can see that actuator length AC is a linear function, but AD and BE are quadratic functions. Now, within the user manual, you'll notice you have this function 8.1 over here. In this case, I don't know why it shows these blocks, but it's essentially F equal to C1 plus C2t plus C3t squared. So this is exactly the function that was given to me. If I have a linear case, I simply drop this C3t squared. So I make C3 equal to 0. So I can easily use type A function to specify those three actuator length functions that were given to me. And I'm going to do this under the infuncts file. So if I head to infuncts.m, then I'm going to define it as f1, which is a funct structure. And then f1.type is going to be type A function. And then I also need to give it the coefficient as input. Now, if I just look at the order of the coefficients, it says I specify C1, which is the constant, C2, which is the part that's multiplied by t, and C3, which is the part multiplied by t squared. And for my actuator lengths, I can see it's already ordered in that form. So I have the constant first, then whatever value is multiplied by t, plus, in this case, I just have 0t squared. So I just have to carry over these values. Right, and to do that, I'm just going to say, so for actuator AC, it's 0.34122. So 0.34122. And then in this case, I'm separating the values with a space, not with a semicolon. And then the next value is 0.0098882. 882. And then lastly, it's just going to be 0.0, since I don't have anything multiplied by t squared. Then I'm going to do the same for actuator AD. So this is once again just a funct struct. And then f2.type is once again a type A function. And f2.coefficient is then equal to 0.44164, followed by 0.003674. And then lastly, we have 5.8753 times 10 to the power of minus 5. And then the same for actuator BE. So this will be funct struct. f3.type is equal to A, and f3.coefficients is then equal to whatever we have over here. So 34017. So now I don't have to find the functions, I just group them together in its list. So f1, f2, and f3. And now I can go back to in joints and I can go and define the relative translational joints or drivers. So I'm just going to create a new section and call this relative translational joints. Okay, so checking back, I essentially need to give it an IP index, a JP index, and an ifunct as input. Now in this case, the IP and JP indices are going to make a difference in the values that are reported back, or rather the vector direction that is reported back. So if I perhaps just open up maybe just a sketcher over here. So if we look at the Gough-Stewart platform that we have, so we have ground over here at the bottom, and then between ground and the platform, we have these actuators situated over here. And I can go and plot this one as well. And then let's perhaps do that point over there. So what that BC will do is if I specify this as point I and this as point J, it will construct the vector in this direction. So point I is always at the arrow end of the vector, and point J is at the rear end over here of the vector. And in my case, it would make sense that I want to rather focus on the forces going upwards onto the platform body over here. So it would be best to rather use point I for these 2 points A and B, and then use point J as the grounded revolute points that we have over here. So then all of the vectors will point upward. Okay, so in an exam situation, I think last year we did ask for the actual calculation. So we're not really interested in the value that you're going to get out, rather than the actual Lagrange multipliers that you utilize to get the value. If we do ask you for the value, we will ask for the magnitude, so that if you define like point I over here, point J over here, it doesn't influence the answer at the end. We just want the actual magnitude, but that would be for something like a short question. In general, we rather want you to just formulate how you're going to get the revolute joint reaction force based on the Lagrange multipliers, what function you're going to use. So, but in general, I think this is a good convention to use when you're working with something like a Gough-Stewart platform. You want to evaluate what the forces over here are going to be on the platform body. So in that case, I want to use point I on the platform body points, and then point J will be on the grounded revolute points that I have. Okay, so to do that, I'm going to set up then joint 10. So this will be J10, which is a joint structure. J10.type is now going to be a relative translation driver. So I'm just going to use that shorthand notation for that. Then J10.IP index is the first one that I want to consider. Now, you might also ask, why do we want to use point A1 and point C0, for example, and not point A2 and point C5? They are at the same points in any case, so what would be the difference? So this has perhaps more to do with the modularity of the problem. If you, for instance, want to create a very simplified mechanism where you only consider the platform body, but you still want to model the actuators, then you would have a single body, body 1, and then connected to ground would be that relative translation drivers. So I can easily, from that situation, remove these bodies over here and just consider the combination of the linear actuators with the platform body, or the relative translation drivers together with the platform body. So I ideally want to use points A1 and then point C0 as well. Right, so I'm going to start off then with my IP index, which is then on the platform body. Yes. So you can, yes, I think you can do that. Yeah, so that would be then be for the for the combined revolute joint. Yeah, I'd say a RevTran would probably work. Otherwise, you can also do you can actually rather do a revolute joint, I think. Oh no, that would be because revolute joint acts between two revolute joints that you have. So you have one at you have one on the ground, but if you remove the bodies, then you don't consider that revolute joint. Yes, so you would use a revolute translational joint. Yes. Yep. All right. So so if we then go over to our points and we just want to extract point AP1 over here, so that is point 4. Then that would be the IP index, and then J10.jp index is then point CP0. So if I go to endpoint, CP0 is the very first point that I have. So that's just going to be 1. And then lastly, I just have to define the function that is applicable to this linear translate, or the actuators. So I'm just going to say ifunct is equal to 1. Okay, so now I can go and do the same for the other two relative translational drivers. Yeah, so I think with regards to if you remove the bodies, you won't actually have to define Revolut translational drivers at all. So you'll only have the platform body, and then you'll have the relative translation drivers. Reason being, you don't have any bodies that you need to connect to one another. So in that case, the only thing that you'll specify is essentially the 2 points on your platform body and the 3 points on your grounded Revolut joints. And then you, in any case, use IP index, JP index, and ifunct to put in those relative translation drivers. Yes. Yeah. Okay. So now with regards to J11, if we look at its point indices, so this would be A1 and D0 that we're focusing on. So this will be still 0.4, but then the JP index will be DP0, so that would be 2. Right, and then I just have to go and update the function as well to 2. This last one's function will be 3. And then its point indices will now be B1 and E0. So if I look at this one, that would be 0.5 and 0.3. I just specify over here 5 and 3. Okay, so now I've defined all of the joints that I need. I have my 6 Revolut joints, I have the 3 translational joints, and then I have my 3 relative translational drivers as well. So now I can just go and group everything together under the in joints, or the joints list that I have. So J1, J2, all the way up to J12. And I can save the script as well. Okay, so now that that is done, just have to check back what the instruction says. So I've now updated in forces, in functs, in joints, in U vectors. And then it says I have to simulate the mechanism for 40 seconds with a reporting time step of 0.4 seconds. Now, before I do that, I just want to make sure that all my joints are specified correctly. So what I'm going to do is just head over to DAP. And you'll notice in this case, the folder has already been assigned as GSB_B, so I don't have to worry about redefining that. It is going to perform an initial condition correction, which is also what I want. Then T final at this stage is set equal to 0.0. So I'm not going to change this to 40 seconds yet. I want to keep it at 0. I just want to see how the setup looks, whether all of the parts are connected as they should be. It shows the number of function evaluations, and then at the end it also runs this post. So yeah, in this case we don't have to go and type post after we run DAP. It will automatically run the post processor, and we can directly extract the results. Okay, but nonetheless, let's maybe do the IC correct as well. So if I go to the analysis IC correct, then here at the bottom, this part was commented out. So I'm just going to uncomment this. I just want to make sure that the values that I get do make sense as well. So once all of that is done, I'm just going to run clear all, close all CLC, type in DAP. Okay, so now it says number of function evaluations is 1. This makes sense since it's a static test. If I perhaps want to check what x dot and y dot's magnitude gives me, so if I say square root and I take this value, so you'll remember that we said the platform velocity is given as 0.01 meters per second. So I just want to make sure that x dot squared plus y dot squared does give me that 0.01. Okay, so this is essentially 0.01, so this is fine, 10 millimeters per second. Now once this is done, I'm just quickly going to run anim as well. Okay, so it took a while now to just generate it, but we can see over here we have actuators 2 and 5, or actuator bodies 2 and 5 connected, 3 and 6 connected, 4 and 7 connected, and we have body 1, which is the platform body, horizontal, and it does sit at the start of this trajectory over here, so that is fine. So if I'm happy with that, I can just say clear all, close all CLC. And then I go back to DAP, and now they said we want to simulate it for 40 seconds with a 0.4 second time step. Now in my case, I'm just going to use a bit of a more coarse time step over here. I just want to check how the actual motion of the system now looks. So I'm going to run DAP. Now it asks for a reporting time step, so let's perhaps do 1 second in this case. Okay, so it took 150 function evaluations. Now if I run anim, I can just press a key over here. And what you'll notice is that it's now essentially following this path that I have. So these dotted lines. In the exam, the animation will most likely run a bit faster. This is not the newest laptop that I have, but I think the computers that you will have available will run these simulations fairly quickly. So you don't have to worry about waiting too long, as long as you just use a fairly coarse reporting time step. And then once you're happy with the actual animation, then you can go and make the reporting time step a bit finer to either generate graphs or to just simulate according to the question. Like in this case, we now use a 0.4 second time step. Okay, so we can see that it now terminated, and it essentially followed that path up to the end, so that is fine. Now I'm just going to say clear all, close all CLC, and I'm going back over here. So the reporting time step, I can change it to 0.4 seconds if I want to, so to perhaps just make that a constant. What I'm going to do is in this if-else statement that I have over here. So this one says, if you're running a static test, don't ask for the reporting time step. Otherwise, do ask for the reporting time step. But in my case, I now know the reporting time step has to be 0.4 seconds. So I'm just going to comment that first line out and say dt is equal to 0.4 in this case. Okay. Right, so now I'm happy with that. Then I can just go to what these questions essentially ask over here. So this was just changing or modifying the input files. And now I want to focus on question 2, which is editing the dap.m file to automatically perform the following calculations. So the automatically tells you that you need to use code to calculate these values. So the very first one is RAX, which is the initial X component of the reaction force at revolute joint A. And this we can see in figure 1. So if we go back up over here, so at point A, we essentially have 2 revolute joints, one between body 1 and 2, another one between bodies 1 and 3. And I need to take both of them into account when I calculate that revolute joint reaction force. So to do this, I'm going to have to utilize the Lagrange multipliers. Now, if I go down over here, I'm just going to say RA underscore X. And I need to go and check the order in which I specified these functions over here. So I started off with revolute joint C. So those would be the first 2 rows in my Jacobian matrix, but also for my Lagrange multipliers. Then revolute D is the next 2 rows, revolute E the next 2 rows, and then the one that I'm interested in first is revolute A1, A2. So those are the next 2 rows. The first row in this case is going to be the X reaction force, the second row, the Y reaction force. So if I quickly check over here, this would be 2, 4, 6, 7 that I want to extract. And then 8 is the Y value. In the case of A1, A3, that would be 9, which corresponds to the X reaction force again. So 7 and 9 are the two Lagrange multiplier indices that I want to use. But I also need to go and take into account the Jacobian. So the Jacobian tells me what the sign of that specific reaction force is going to be. Now, if I head back to dap.m, I can actually run this one. So if I say dap, all right, I think it actually just skipped over this last line, which is fine. I'm just going to comment that out for now. So if I firstly focus on Lagrange multiplier 7, which is then the A1, A2 connection. And I'm just going to say Lagrange multiplier. I'm just going to print it out for the first one. Then I get this minus 2.7409. Now its corresponding Jacobian sign will be 1, and I think it's 7, and this is then on body 1. So I'm considering the reaction forces on body 1 in this case. So that would then be 1, I think. And I can see in this case, I do indeed get this answer equal to 1. So that simply means that the reaction force caused by the revolute joint between bodies A1 and A2, or point A on body 1 and body 2, is then minus 2.741 Newton, since I just multiplied by 1. I can also go and check for Lagrange multiplier 9. And in this case, it's 3.7063. And then if I check the corresponding Jacobian, that is also 1. So now I can easily go and calculate the resultant reaction force due to these two revolute joints. That would be simply the Jacobian 171 multiplied by Lagrange multiplier 17 plus the Jacobian 191 multiplied by the Lagrange multiplier 19. Okay, and I use 1 in this case since they did ask in the exam paper for the initial X component of the reaction force at revolute joint A. Right, now I just have to carry this over to RAX. So this would be, in this case, Jacobian initial point, the 7th column that I'm considering, and this is for body 1 in the 1 direction, or the X direction, so it's index 1. I just say dot multiply Lagrange multiplier 17 plus, and then I do the same for index 9. Right, so that was the first calculation. I can perhaps just take away the semicolon over there as well. Then the next one is just RAY. So these are the initial Y component of the reaction force at revolute joint A. So now I just consider in the Y direction, still on body 1 that I'm interested in. Okay, and in this case, it will now just be 1 increment higher than the X directions that I've considered. So this would be Jacobian 182, since I'm now working in the Y direction, multiplied by 8 over here, and then 110 multiplied by 110. So I'm actually just going to copy this one over. And then this would be 18, just change this to 2 as well, 10, 2 over here, and 10 over here. And then I just have to remember to update this naming convention as well to RAY. Then I'm going to do the same with regards to RBX and RBY. So at point B, this is perhaps a bit easier since you only have a single revolute joint between body 1 and body 4. So I only need a single multiplication between a Jacobian and a Lagrange multiplier. But RBX is then the initial component of the X reaction force at revolute joint B. So to go and find this, I just head back to my in joint, and the one that I'm interested in now is the revolute joint over here. So if I check, that is 2, 4, 6, 8, 10, in this case 11 and 12 are the x and y components that I want to consider. So to go and find this, I can over here just say Lagrange multiplier 1 and then 11. Okay, so that would be the RBX value. I can just go and check Jacobian as well. So if I say this, and this is in the one direction again, so then I still get 1 out, so that's fine. And then in the y direction, it's going to be Lagrange multiplier 1, 12, and then Jacobian 1, 12, 2 is 1. Okay, so it's identically equal to the Lagrange multiplier, since I just have multiplied by 1 in this case. But I'm in any case going to include it in the formulation. So if I say over here RB underscore x, that would be Jacobian 1, 11, 1 dot multiplied by Lagrange multiplier 1, comma 11. Then for RBY, it will simply be 12 and 2. So I just change this to 12, make this 2, and then this will be 12 as well. Okay, so these are all of the Revolute joint reaction forces that I then have to consider. I can quickly go and say clear all, close all CLC. I can run DAP, and since I didn't place a semicolon at the end, it should print out these reaction forces due to the Revolute joints. So we can see RAX is now 0.97, RAY and RBX are negative. I should maybe just update this as well, so there should be RBY. But if we look at the printed value, this is RBX and this is RBY. So both of the Y reaction forces are negative in this case. Then for the next two questions that I have over here, sigma Fx and sigma Fy. So these are the initial sums of the external forces acting in the X and Y directions on body 1. So sigma Fx is fairly easy to calculate since I now already have the reaction forces available. All that I actually need to say is Rax plus Rbx. Sigma Fy is a bit more complex in the sense that I need to take into account firstly the weight of the body, and then I also need to take into account that friction force that I considered. Sigma Fx I think will also take into account the X friction force. But if we now go and define it, I can say over here sigma Fx is going to be Rax plus Rbx, and now I just have to go and check back what the X friction force was that I specified. So this was minus 50. If I head to DAP, I simply say over here minus 50.0. And then for sigma Fy, I simply take into account Ray plus Rby. And then I need to minus the in forces, so this 86.603. And then also minus 3 times 9.81. So this is simply mass multiplied by the gravitational constant. If you go to in bodies, you'll see body 1 is 3 kilograms. So that's why I use 3 times 9.81. Okay, and I think this is then basically the two functions that we wanted to specify over there. So I can once again go clear all, close all, run DAP. Since it already runs the post processor, it's going to give me all of the corresponding forces that I need. So Rax, Ray, Rbx, Rby, and then the two resultant forces Fx and Fy as well. Right, so I think this was then, yes. Sorry, which forces? Yes. No, so you'll need to still account for that. So that's essentially why when we calculate sigma f x and sigma f y, we include the friction forces over there. The reaction forces itself is just focused on the actual joint itself. So you still need to account for the external forces when you do that calculation.
And the two-dimensional matrix.
Yes.
That first index, is that time?
Yes. So first index.
Isn't there also a J matrix that we just reference the last two indices instead of worrying about the time change?
Yes, I think you can. It's a I think there is one. Let me just check. It's also for the Lagrange multiplier. I think there's also one. So I think it's this lambda. That's one of them, and then Jacobian. Oh, okay. Let's see. Further up. But yeah, I think there is so if you look at the lambda case, this one corresponds to the Lagrange multipliers. I think it's the initial. Just have to maybe check. Okay. So we check over here. So yeah, so there does appear to be a bit of a difference between the two. I see this one is minus 1.641. This one is minus 2.7408. So according to me, they should have corresponded if this lambda gives you the initial point. So my suggestion would rather be to use the one that is generated as a function of time. So the three-dimensional cases. So for your lam, which is then the one that you want to use, you also have 101. So in this case, it's your time by 21 is then based on the number of joints that you have. So in this case, we have 21 constraints that are imposed by the different joints. And then for Jacobian, it's also time by, and then you have 21 by 21. So the first 21 is then with regards to the constraint number. So that always corresponds to the Lagrange multiplier that you are referencing. And then the last 21 over here is then dependent on the number of bodies that you have. So each of them have 3 coordinates. So it's 7 times 3 in this case, which also gives you 21. But essentially that will then be whether you're working in the X or Y direction or around the Z axis, and then also which body are you considering. In our case, we considered body 1. So we're considering basically that first column, the X, Y, and Z direction. So 1, 2, and 3 are the indices. Yes. Yeah. Okay, so any other questions with regards to this? Okay. All right, so this is then the dynamic analysis, the pure dynamic analysis that we considered. I'm going to jump into the optimization in the next lecture. I feel that we covered quite a lot of content today, so I think maybe taking a bit of a break or just giving you a chance as well to try the optimization on your own would be a good idea. But essentially, this is the same format that we will use for the upcoming exam. So you'll also have some section on a dynamic analysis. Once the dynamic analysis is performed, then we'll move on to an optimization analysis that you will do. They will probably be interconnected as well, but we do give you enough time during the exam to sort of get everything ready or good for questions 1 and 2, and then you can focus on question 3. So the breakdown of the marks as well in this case, question 3 was 40%, and then questions 1 and 2, which are just the dynamic analysis, was the other 60%. Question 3, I think we also had a few short questions, so there might also be short questions for this upcoming exam. Last year we did it with AMS, so you had to use like an OCR form to write it down. This year we'll probably just rely on exam books. You'll just write your answers in over there and we'll mark it manually. I think that's a bit easier in any case. Okay, but that is then everything for this first part of the 2023 exam. So I'll then see you again next week for the optimization question. Right, thanks.